Good morning students, let's continue the chapter thermodynamics. In previous lecture, we have discussed some assumptions which we require for the thermodynamic processes. In the first assumption, we assume that the processes, they are the reversible processes. What is a reversible process? A process in which the path is retraced in reverse direction. Then that is known as the reversible process. Again, we assume that the thermodynamic equilibrium is always there, and for that we consider the quasi-static system. What is quasi-static system? Quasi-static system is a process in which the state variables, which are the state variables, the pressure, volume, temperature, these are the state variable. The changes in the state variables occur infinitesimally slowly. When the changes occur infinitesimally slowly, then the state variables, they are continue in equilibrium. The system does not go in equilibrium. And lastly, we assume that the ideal gas equation is applicable for the systems. And now let us classify the thermodynamic processes by keeping the variables like temperature, the pressure, the volume kept constant. When the temperature is kept constant, then the process is known as isothermal process. When the temperature of that system is kept constant, then that process is known as isothermal process. When we kept the pressure constant, then that process is known as the isobaric process. In isobaric process, we kept the pressure constant, and the third one is the volume, that is kept constant. When the volume is kept constant, then that process is known as the isochoric process. Then the next process by keeping the heat constant means the heat is not allowed to exchange between the system and surrounding, then that is known as the adiabatic process. In adiabatic process, the heat is not allowed to exchange between system and surrounding. And lastly, we are going to discuss the cyclic process. So in this way, these thermodynamic processes are get classified. This isothermal process is also known as constant temperature process. This isobaric process is also known as constant pressure process. This isochoric process is also known as the constant volume process. And this idea, in this adiabatic process, the heat is not allowed to exchange between the system and surrounding. And in the last process, that is cyclic process, it is cyclic. It returns the system back to its initial state. Returns the system to its initial state. When that system returns to its initial state, then that process is known as the cyclic process. Now let us see the examples of these processes. The isothermal process. The example is melting of ice. In melting of ice, the liquid and ice, they are coexist. The example of this isobaric process is the boiling of water. The water is boiled at constant pressure. Then let us see the example of this isochoric process. When the ideal gas is heated at constant volume, then that is known as the isochoric process. So these are the examples of these processes. Now let us see one by one these processes. First of all, let us see the isothermal process. First process is the isothermal process. In this isothermal process is also known as the constant temperature process. In this, the temperature is kept constant. Now let us see the definition of this isothermal process. A process in which change in pressure and volume takes place at constant temperature. The process is known as isothermal process. This is the definition of this isothermal process. In isothermal process, there is change in pressure, there is change in volume. The pressure and the volume, they are get changed and at constant temperature. When the temperature is constant, then the Boyle's law is applicable. What the Boyle's law states? The pressure of given mass of gas is inversely proportional to volume at constant temperature. This is the Boyle's law. According to this Boyle's law, PV is equal to constant. If Pi and Vi, these are the initial pressure and volume of a gas, and if they are get changed to Pf and Vf, then according to Boyle's law we may say that Pi Vi is equal to Pf Vf. Now let us see this isothermal process. This isothermal process is occur at constant temperature, and that's why we have to consider the cylinder, which is a good conductor, so it can exchange heat between system and surrounding. And as we have assumed that it consists of an ideal gas, and the process occur infinitesimally slowly. The heat is provided to the system in very small steps, in very small amounts, and that's why the force which is exerted on this piston is infinitesimally small, and in that case the work done is also infinitesimally small. And now let us see the thermodynamic of this isothermal process. Let us consider del W be the infinitesimally small work done. This infinitesimally small work done, del W is equal to P into dV, where this dV is infinitesimally small change in volume. Now we are interested to find the total work done in the process. The total work done W is equal to integration of dW, where the limits of integration are from initial volume Vi to the final volume Vf. Now let us substitute this value in this equation. What we get? The integration of dW, where the volume changes from Vi to Vf into P dV. Now according to ideal gas equation, we know that PV is equal to nRT. From this we get the value of P is equal to nRT by V. Let us substitute this value in this equation. We get the equation for work done W is equal to the limits of integration are from Vi to Vf. P is equal to nRT upon V, and the variable is del V. Now the variable is V, these are the constants, so outside the integration we get W is equal to nRT integration of the limits are from initial value Vi to final value Vf dV upon V. We know that integration of dx upon x is equal to log of x. Same thing is here. This is the integration of dv upon v. So it is equal to nRT dv upon v, means dx upon x is equal to log of v, and the limits are, the lower limit is vi and the upper limit is Vf. These are the limits. So from this what we get? W is equal to nRT. Let us substitute the upper limit first. Log of v is equal to Vf minus, let us subtract the lower limit, v is equal to Vi. We get this. We also known as log of A minus log of B is equal to log of A upon B. Same thing is here. We get this W is equal to nRT log of A is Vf upon Vi. We get this equation for the work done. Now we know that the first law of thermodynamics, change in internal energy del U is equal to Q minus W, and as the temperature is constant, the temperature, there is no change in temperature, the change in internal energy is also equal to 0. So this 0 is equal to Q minus W, which implies that this Q is equal to W, and as this Q is equal to W in thermodynamic process, we may say that this heat supplied is equal to work done. So this Q is equal to W is equal to nRT log of Vf minus Vi. From this equation we may say that the heat which is supplied to the system is totally utilized by the gas to do work in pushing that piston in upward direction. So this is the thermodynamic process. Now let us see its PV diagram. The PV diagram of this isothermal process. This is the pressure axis and this is the volume axis. Suppose this is the initial state which is having pressure Pi and the volume Vi. So it changes by this path to the final volume Pf and the final pressure Pf and the final volume Vf. This is known as the isotherm because it is occur at constant temperature. So this is all about the isothermal process. Thank you.